Hello everyone, welcome to this online course on material science, and I'm Dr. Imtiaz Ahmed. This is module 1 of the course and the third lecture on magnetism. In this lecture, I want to discuss some of the important physical quantities of interest that are important in understanding different aspects of magnetism. The first quantity that I want to discuss here is known as magnetic vector potential. To understand what this quantity is, you have to recall one of the Maxwell's equation from your second year electromagnetism course, which says the divergence of the magnetic field is 0. So magnetic field is a three-dimensional vector, and this del operator also is a three-dimensional differential operator, we know. So what this equation is telling us that magnetic field is divergenceless. But if you also recall from your vector calculus course, there is a theorem which says the divergence of curl of any vector is 0. So since B is a vector, its divergence is 0, it's implying that B should be written as a curl of some vector quantity. And the quantity that one uses to define B is the magnetic vector potential. So this is how one can introduce the concept of vector potential in electromagnetism. So having this quantity in hand, now I want to define another important quantity which will be useful to understand diamagnetic behavior of the solid. So this is known as the canonical momentum. So if you recall in the classical physics, the momentum of a particle is very simple, right? You take the mass of the particle and multiply with its velocities. It's m times v. But we want to define a canonical momentum, p, which is mv times the charge of the particle times the magnetic vector potential. So if you look in these two definitions, you can see there is an extra QA in this definition. So it will be good if you can replace the P with P minus QA, because it's as though we are trying to get rid of this vector potential term QA. So whenever you see P in some expression, we should be replacing it by P minus QA. This is a way to understand the canonical momentum. There are other ways which are a bit, I would say, require more advanced understanding of minimum coupling between the external field with the charged particle. But I don't want to bring that idea. This should be enough to understand what we'll be discussing in the lectures to come. So the message is, if you see the P, replace it with minus QA. So for electron, let's say for electron, the Q is what? Minus E, right? So for electron, if I see P, I will replace P by P plus E times the vector potential. You remember this fact because this will be important when we study the quantum mechanical behavior of diamagnetism. Okay, so having said that, now I want to really introduce the different types of magnetism that can occur in solid, right? So here are the types of magnetism. We have diamagnetism, we have paramagnetism, ferromagnetism, then antiferromagnetism and ferrimagnetism. So to understand the first two, consider that we have some solid, right? And inside the solid, we have different moment, magnetic moment. And don't worry what causing this moment, but the only consideration here, there are a number of magnetic dipole moment inside the solid. And we are trying to apply an external magnetic field through the magnetic field intensity vector H. So the idea is that what is the effect of this magnetic field on this solid, right? So the question can be answered by the quantity which I have defined in previous lectures. The susceptibility is defined as the ratio of the magnetization vector to the applied magnetic field. So now, if the value of chi is less than 0, which means these moments, for example, let's assume that this is the direction of the external magnetic field. Now, if chi is less than 0, then the magnetization and the applied magnetic field is out of phase. What it means that the materials, the magnetic moments of the materials tend to anti-align, right, to the applied magnetic field. So this object will be repelled by the magnetic field. These materials are called diamagnet, right? So it says that a diamagnet is a material with a susceptibility less than 0. It means the resulting magnetization is in the direction from the opposite direction from the applied field. Now, for paramagnetic behavior, chi is greater than 0. It means the magnetization inside the solid and the applied field are in phase. So the moments inside the solid will try to align the external magnetic field. Those materials are called paramagnet. So the diamagnet and paramagnet requires an external probing field, right, for their definitions. But the rest three, like the rest of the three, like ferromagnetism, antiferromagnetism, and ferrimagnetism, for them, one important thing to understand is that we don't need any external magnetic field. For some reason, we will see in the lectures in the future that what causes this alignment, but the central point I want to emphasize here is that for ferromagnetism, antiferromagnetism, and ferrimagnetism, we don't have to apply any external magnetic field. But even then, in the absence of magnetic field, the magnetic moments inside solid order themselves spontaneously. So it's called spontaneous ordering. So another important term is that for this sort of magnetism, spontaneous ordering is observed. Of course, there are deep reasons why this ordering occurs, but right now the message is we don't need any external magnetic field to align the moments. The moments will align themselves spontaneously. And depending on the alignment, we divide this magnetic ordering into three different types. First is ferromagnetism. To understand this, let's assume a two-dimensional lattice, and these points are lattice points where something is sitting and making a magnetic dipole moment. It could be anything, an atom, it could be an ion, or anything. So important point is the species sitting in these points making a magnetic dipole moment. And let us assume for some reason all of these moments are aligned with each other. Then you can see the resultant magnetic dipole moment will be enormous, right, in this direction, because they're adding up with each other. So this sort of materials where the magnetic moments aligned spontaneously in parallel direction are called ferromagnetic materials. Okay, and then there is another class of material where the similar thing happened, but this ordering is kind of opposing in the nearest neighbor side. So if the moment in this side is in this direction, the neighborings are opposing it. So what happens if you consider like this is a unit cell or some sort, you can see two are pointing in this direction, two are pointing in this direction. So the net magnetization is 0 in this unit cell. So even there is spontaneous alignment because the neighboring moments anti-align, there is no net magnetization here. So this sort of materials are called antiferromagnetism. And the last of its kind, I think, is defined in such a way that what happens is that in the different lattice points, in the neighboring lattice points, the atoms of the species are different. So for example, let's say here there is a bigger atom or bigger ion there and making a bigger ionic contribution at that point. But in the neighboring side, the atom is smaller, or the ion is always smaller, and then its magnetic moment is small but anti-aligned with the neighboring one. So in this case, if somebody asks you, if this is the unit cell, right, then what will be the magnetization? If you look carefully, two of these big moments are pointing in this way, two of the small moments are pointing this way. So there will be a cancellation, but it will not be a net cancellation. So in the unit cell, we will have some net magnetization. This sort of materials are defined as ferrimagnet. Okay, that's about it. If you want to read about these things in details, there are two references I would suggest. One is the usual one that I've been saying for the last few lectures. This is the new one, which is the Oxford Solid-State Basics in its first edition from Stephen Simon from Oxford University Press. I think that's about it, and in the next lecture I will start from the understanding of diamagnetism. Thanks for listening.